All right, hello everybody. Today we're looking at Objective 1 for our Geometry B review. And the topic for Objective 1 is similarity. Okay, in geometry, similarity is the idea of we have two figures that are different sizes but still the same shape. Okay, think scale drawing, think scale model, think scale map. So we'll see a lot of different real-world applications to this idea. And it's an extremely important one as far as what you should take out of geometry. So let's get going talking about similarity. All right, now there's a few concepts we need to talk to before we can get to actual similarity. The first one is the idea of a ratio. Okay, a ratio is just a comparison of two quantities by division. So in other words, it's a fraction. And you can write the ratio of two numbers, A and B, where B is not equal to 0, because you can't divide by 0, in three ways. We could say A over B as a fraction. We can say A colon B, which would read as A to B. Or we can just say A to B. All three of these mean the same thing. Divide A by B. That's a ratio. So first problem we're going to look at is involving writing a ratio. So let's look at the situation. It says a model is made of a car. The car is 9 feet long, and the model is 6 inches long. We want to know what's the ratio of the length of the car to the length of the model. Okay, so we have two geometric objects, a car, the actual car, and a model. And again, if we have a scale model, this is the idea of similarity. And what we want to do is we want to come up with a ratio that's going to help us compare the size of the car to the model. So I want to make a fraction with the car on top, model on bottom. Okay, just staying in the same order as it's given to me in the question, car to model. Okay, the length of the car is 9 feet. And the length of the model is 6 inches. So I have a ratio of their lengths, but the problem is since one measurement's in terms of feet and the other one's in terms of inches, if I reduce this fraction, it's really not going to make a lot of sense to me. Okay, it's not going to give me a meaningful number. So what I'm going to want to do is I'm going to either want to convert the 9 feet to inches or the 6 inches to feet. Either way will work. I'm going to do the 9 feet to inches just to keep all my numbers whole numbers here. And we can do that by multiplying by 12, because there's 12 inches in a foot. So that's going to give me 108 inches, all right, over 6 inches. And now what I can do is I can divide 108 divided by 6 is going to give me 18. So I could write this as a ratio of 18 to 1. And what this number is telling me is that the car is 18 times the size of the model. That's kind of the idea of a scale factor, which we'll talk about in a few minutes. Okay, but anyways, that's how you write a ratio of two quantities. Okay, you have to first make sure they're in the terms of the same units, convert if you need to, and then reduce it. All right, so that's problem 1, part A. Now your note guide has a part B in it. Take a minute, pause the video, run through part B on your own, so we're going to give you a chance to practice this before you move on. And then throw a hand up in the air to check the answer. Somebody come around and check it, make sure you're good before we move on to the next question. So why don't you go ahead and give that a shot here. The next thing we're going to talk about is the idea of an extended ratio. That's just something that compares 3 or more numbers. And we could write it as A to B to C. And really what it does is it just sums up the ratio of A to B, B to C, and A to C, kind of all in one expression. So let's take a look at using an extended ratio. Okay, problem 2, part A says, the lengths of the sides of a triangle are in the extended ratio 3 to 5 to 6. The perimeter of the triangle is 98 inches. We want to know what is the length of the longest side. Okay, for this type of problem, we're going to want to set up an equation. And what we're going to do here is going to work anytime I have a ratio of the parts of something, and then also the total. So in this case, I have the ratio of the sides and the perimeter of the triangle, so the total of the sides. What I can do is I can make an equation by attaching x's to each number in the ratio. So we could say 3x plus 5x plus 6x, and then set that equal to the total, set that equal to 98. What I have now is a pretty straightforward equation to set up and to solve. Okay, well, if I combine my like terms, 3 plus 5 plus 6x is going to give me a 14x. So 14x is equal to 98. And I can divide both sides of the equation by 14 to get the x by itself. Okay, 98 divided by 14 is going to give me a 7. And then 7's not the answer. The answer is I want to know what's the length of the longest side. So what I'll do for that is I'm going to take the 6x part of my equation. Okay, because that corresponds with the longest side in this 3 to 5 to 6 ratio. And I'll plug my 7 into the 6x. So we could say my longest side is equal to 6 times the 7 we just found. Okay, 6 times 7 is just 42. So I know the longest side of that triangle is just 42 inches. All right, so there's an example of using an extended ratio for some problem solving. Now I could do the same thing with a simple ratio of two quantities, or I could expand that out to 4 or more. But again, basically anytime I know the ratio pieces come in and the total, I can set up an equation like this, solve for x, and then plug the x back in to figure out whatever I'm looking for. Okay, once again, there's a part B in your note guide. Go ahead, pause the video, run through that one, get your answer checked, and then you can move on to the rest of the lesson. So the next concept we're going to talk about is the idea of a proportion. I'm going to say a proportion is just an equation that states that two ratios are equal. So for example, if I have the ratio 1/2, I know that's equal to 3/6. Okay, half, 3/6 are equal ratios. So that is a proportion. And what we're going to be interested in doing is solving the proportion. Okay, if we have some variables in here, like let's say I didn't know this was a 3, it was an x, I want to figure out what x value makes that proportion true. To do that, I'm going to use something called the cross product property. It just says that in a proportion, the products of the terms that are diagonally across from the equal sign from each other are the same. So in this case, if we have the proportion A over B equals C over D, the cross products would be A times D and B times C, and this property is saying that these two cross products are equal to each other. Okay, essentially what I'm doing here is just canceling out fractions. If I take my proportion here and multiply both sides of it by 6, that would cancel the 6's on the right. And then if I multiply both sides by 2 as well, whoops, that would cancel the 2's on the left. And what we're left with then is 6 times 1 is equal to x times 2. My two cross products are equal. And then from there I can solve the rest of the equation. We get that same x equals 3. Okay, so that's how a proportion works and how the cross product property works. So let's take a look at solving some ugly proportions. Okay, problem 3, it says, what is the solution of each proportion? And for part A, we want to figure out what value of y I could plug in that make these two fractions equal to each other. So to do that, we will cross multiply. We'll find the cross products. So I'm going to look at 9 times y, which is just 9y. And we'll set that equal to the other cross product, okay, the y plus 4 times 3, which I'm going to write as 3 times parenthesis y plus 4. And I need the parentheses because I want to multiply that 3 by my entire numerator here. And that's going to help me remember to distribute the 3 to both the y and the 4. So we can rewrite this equation as 9y is equal to 3y plus 12. Okay, so we got the cross multiplying done. And then once you do that, you're going to be down to a simple linear equation. Okay, something easy to solve in a few steps. Now, simpler proportions, you can just cross multiply and divide. Here we've got a little more going on with that. We've got to get the y by itself. So I'm going to subtract 3y from both sides of the equation. Okay, it's going to cancel the 3y on the left, or the right, leave me with a 6y on the left is equal to 12. And then I'll divide both sides by 6, which will give me y is equal to 2 for a solution of my proportion. Okay, I can always check and make sure that works. If I take the left side of my equation and go 2, which is the 2 I found, plus 4 over 9. Okay, so replacing the y with a 2, that's going to give me a 6 over 9, which reduces down to 2/3. On the left side, if I replace the y with a 2, I get just 2/3. Whoops. So yeah, y over 3 is the same as 2 over 3. Yet we get that same 2/3. Okay, so I know I found the correct solution. Alright, part B has another one of these kind of uglier proportions to solve. Why don't you take a minute, pause the video, work through that one, and then don't forget to check your answer before you move on. So now that we've talked about how to set up and write a ratio, how to solve a proportion, we can finally get to the idea of similarity. I'm going to say similar figures have the same shape, but not necessarily the same size. So once again, think scale model, think scale diagram. Those are examples of similar figures. And as far as how we'll make that happen, okay, in geometry with our polygons, we'll say that two polygons are similar polygons when they have congruent angles and proportional lengths of corresponding sides. Okay, so down below, if I say that polygon ABCD is similar to, and the squiggly line here is our similar symbol. So if ABCD is similar to polygon GHIJ, we said that number one, that means that the corresponding angles are congruent. So as in angle A will be congruent to angle G, B will be congruent to H, same thing with C and I, same thing with D and J. And then also the corresponding sides lengths are proportional, meaning that if I look at the ratio of AB over GH, that's going to be equal to all my other ratios, BC over HI, also equal to CD over IJ, also equal to AD over GJ. Okay, all of those ratios are going to be proportional. They'll be equal to the same thing. Okay, that thing, that number they're equal to is the scale factor. I'm going to say the scale factor is the ratio of corresponding linear measurements of two similar figures. Okay, so that scale factor is going to tell us how one figure compares to the other. And for them to be similar, we have to get that same scale factor when we look at any set of corresponding sides. Alright, so let's start working with this idea of similarity. First thing I want to do is look at polygons and determine whether or not they're similar to each other. And that's what we're doing in problem 4. Part A, are the polygons similar? Is triangle ABC similar to triangle FED? And to figure that out, what we need to do is check and see if all the corresponding angles are congruent, and then if all the corresponding sides are proportional. So let's check the angles first. both these triangles have a right angle, so that's one angle down. They both have a second angle marked congruent. Now that means that the third angles also have to be congruent. Okay, because both triangles' angles are going to add to 180, I know that if two of the angles are congruent, the third angles have to be also. Okay, so for this one, the angles work, the angles check out. What I want to check next are the corresponding sides. So for example, if we start off with the smaller sides and look at DF over CA, okay, DF over CA is equal to 16 over 8, which reduces down to just 2. What I need to check and see then is that if my other sets of corresponding sides reduce to the same thing. So let's look at the medium sides next, FE and AB. Okay, we could write that as 30 over 15. That reduces down to a 2 as well. Last set of sides, DE over CB. Okay, 34 over 17 is also going to reduce down to a 2. Okay, that's what we mean when we say all the corresponding sides are proportional. They all reduce to the same number, to the same thing. And then that 2 is also my scale factor. Okay, I can tell by that that the triangle on the left is twice the size of the triangle on the right. Okay, so for this one, are the polygons similar? Yes. All the corresponding angles are congruent, and all the sets of corresponding sides are proportional. Let's take a look at part B together as well. So are the polygons similar? We need to check the angles first. Now, all 4 angles for both these polygons are right angles, so we know the angles are good. And next thing we'll do is we'll look at the corresponding sides. We'll look at LO over RS. Okay, which is equal to 10 over 16. And both 10 and 16 are divisible by 2, so I could rewrite this as 5 over 8. What we'll do then is we'll check the other sets of sides, see if they reduce to the same thing, see if they're proportional. And we run into a problem for this one. When I look at ON over TS, I end up with a 4 over 6, which reduces down to 2/3. Okay, both 4 and 6 are divisible by 2. We get the 2/3. Okay, so since these do not reduce down to the same number, for an answer for this one, I'd say no, the sides aren't proportional. Okay, so to be congruent, not congruent, but similar figures, we need all corresponding angles congruent and all corresponding sides proportional. They all need to reduce to the same thing. All right, so next thing we're going to do is use similarity to solve for parts of polygons. In problem 5, we have ABCD is similar to EFGD. Okay, so what that's saying is that these two trapezoids here are similar. And just that simple statement tells me that all the corresponding angles between these two trapezoids are congruent, and all sets of corresponding sides are proportional. So what I can do is if for part A I want to find the value of x, I can use proportions to figure out what this x is. So what I'm going to do is I'm going to make a ratio with x and the side that corresponds to it. So I'm going to write the ratio x over 7.5. And we know that's going to be equal to any other ratio of corresponding sides for this trapezoid. So what I can do then is I can use the sides I know, the 6 and the 9, to write a proportion. We'll put the 6 on top because the 6 and the x are both the smaller sides of the smaller trapezoid. And the 9 on the bottom, that matches up with the 7.5. They're both the sides of the larger trapezoid. And then I have a proportion I can solve. I can simply cross multiply and divide. Okay, cross product, 9 times x is just a 9x. Okay, is equal to the other cross product, 7.5 times 6. When I do that, I get a 45. So we cross multiply, then we can divide both sides by 9. And we end up with x is equal to 5. Okay, for a side length FG. Okay, so that's how we can use proportions to solve for missing parts of similar polygons. Now, the way I set this up here isn't the only way I can set my proportion up. I could have also said x over 6 is equal to 7.5 over 9. Kind of do right side of the smaller over left side equals right side of the bigger over the left side. Okay, I could have done the same proportion and flipped it upside down. 7.5 over x is equal to 9 over 6. Okay, there's a few other ways I could rearrange this. Just basically as long as kind of your left and right, up and down match up as far as which pieces you're talking about, you'll get a correct proportion. All right, part B, you're solving for y. I want you to take a minute, pause the video, work through that, and then check your answer before you move on. All right, so next up, let's apply this idea of similarity to a real-world situation. Okay, problem 6, part A says, a scale drawing of the Golden Gate Bridge uses the scale 1 centimeter equals 200 meters. If the main span of the bridge is 6.5 centimeters long in the drawing, how long is the main span of the actual bridge? Okay, so using this information, I can set up a proportion. I can use my scale factor to write 1 centimeter over 200 meters. And then we can set that equal to, we know that the main span of the bridge in the drawing is 6.5 centimeters. So I'll put that 6.5 up top with the 1 centimeters from the scale. And then I want to know how long is the main span of the actual bridge. We'll call that our x. Okay, so there's my proportion using the scale and then the dimensions I'm looking at. And then once again, solve the proportion. We can just cross multiply and divide. X times 1 is just an x, is equal to 200 times 6.5. The other cross product, which is 1,300. All right, so we can say 1,300 meters long. Okay, part B has another real-world situation. Take a minute, pause the video, set that one up, give that one a shot, and then again, check your answer before you move on. Then the last thing we're going to look at is some shortcuts for proving triangles are similar. Okay, it's actually kind of a pain in the butt to prove polygons similar. You have to check out all their angles and all their sides to make sure all the angles are congruent and all the corresponding sides are proportional. But with triangles, there's going to be some shortcuts. Okay, we have 3 of them. Here's what those are. First one's the angle-angle similarity postulate. It just says that if 2 angles of one triangle are congruent to 2 angles of another triangle, then the triangles are similar. So if 2 out of the 3 angles match, we'll say these triangles are similar to each other. We also have the side-angle-side similarity theorem. It states that if an angle of one triangle is congruent to an angle of a second triangle, so we have congruent angles, and the sides that include the 2 angles are proportional, so as in AB over QR is equal to AC over QS, okay, the sides are proportional, then the triangles are similar. Okay, so if we have proportional side, congruent angle, proportional side for 2 triangles, we'll say that's all we need to know to say the triangles are similar. And then last one, the side-side-side similarity theorem. It just states that if the corresponding sides of 2 triangles are proportional, then the triangles are similar. So if all three sets of corresponding sides are proportional to each other, if they all have the same scale factor, then we get the triangles are similar. In problem 7, we're going to take a look at each of those kind of shortcuts individually and show you how you can use them to check and see whether or not triangles are similar. So it says, are the two triangles similar? How do you know? In this case, we want to know if triangle JKL is similar to triangle PQR. And for this one, since they gave me just angles, the shortcut I'm going to be looking for is the angle-angle similarity shortcut. And they gave me one set that match up. I've got 70s on both these triangles. What I need to check and see is if I have another angle congruent. And if so, we can say they are similar by angle-angle. If not, we know they're not similar. So the way I can find that is, let's say we want angle K. In a triangle, I know that all three angles have to add to 180. So to find the third angle, I can take 180 and subtract 30 and subtract 70. And what I end up with then is angle K is equal to 80 degrees. Now the issue here is that Q is not 80 degrees, Q is 85. Now I could do the same thing and find angle P. I could say that angle P is equal to 180 minus 70 minus 85. That's going to give me a 25 degrees. Okay, not the same as this 30. So what I see here is that this is no, the angles aren't congruent. All right, therefore these triangles aren't similar. Okay, if the angles were congruent, we could say the triangles are similar by angle-angle, but since it didn't work, we'll say no. Okay, in part B, same idea. Are the two triangles similar? How do you know? So we want to see if triangle KLP, kind of the smaller triangle here, is similar to triangle KMN, the larger one. Now this one I'm given the lengths of two sets of sides. And then the trick with this one is also these two triangles are going to share angle K. So what I have then is I have two triangles with an angle congruent, and I know the lengths of the sides that include that angle. So what I'm going to look at is I'm going to see if those sides are proportional. So we'll look at KL over KM. All right, KL is 8. Km is going to be 8 plus 2, which is 10. All right, 8 and 10 are both divisible by 2, so that's going to reduce down to a 4/5. And then what we need to look at is Kp over Kn to see if we get the same thing. Kp is 12. Kn is 12 plus 3, which is 15. All right, both 12 and 15 are divisible by 3. It reduces down to 4/5 as well. Okay, so what I have is proportional sides surrounding a congruent angle. Therefore, are these triangles similar? I can say yes. All right, by SAS similarity, we use the side angle side similarity theorem. Let's take a look at one more example of determining whether or not triangles are similar, okay, using our shortcuts. Now this one I'm not given any angles, so I know I can't use the angle-angle similarity or the side angle side similarity, but I am giving all three sets of sides. So what we can do is compare them and see if they're proportional and test it with the side-side-side theorem. Okay, so let's look at the smallest sides first. We'll look at 6 over 9. That reduces down to 2/3. Okay, if we go with the medium sides, 7 over 12. Okay, we run into an issue right away. That doesn't reduce. Okay, it doesn't reduce at all, much less down to 2/3. So this one, without even checking the third set of sides, well, I suppose we can check it. 10 over 15 does reduce to 2/3. Okay, but since I don't get the same thing for all three sets, this one kind of messes me up. We'd say no, these triangles aren't similar. Okay, if I did get the same thing for this kind of middle set of sides, then we could say yes by SSS, but since I didn't, that's why this one's a no. And the last thing we're going to look at for this lesson is a nice practical application of similar triangles. Okay, it says that in a garden, a bird bath that is 2.5 feet tall casts a 1.5 foot shadow. At the same time, an oak tree casts a 90-foot shadow. We want to know how tall is the oak tree. Okay, so we have a bird bath which is 2.5 feet tall and casts a 1.5 foot shadow. And at the same time, we have an oak tree. We're not sure how tall it is, but it casts a 90-foot shadow. And I'm going to say we can use similarity to figure this out, and here's the reason why. The shadows are made by the sun hitting the top of the figure and coming down to the end of the shadow, making triangles. I'm going to say both these triangles are right triangles. And the trick is as long as you make these measurements at the same time of day and in the same location, the angle of elevation to the sun will be congruent for both of these triangles. So we have then our two triangles with two sets of angles congruent. So by angle similarity, I know that these triangles are similar to each other. Therefore, their sides are proportional. We can set up proportions to solve for this missing height x. Okay, I'd recommend set up that proportion just the way you see it. We can say 2.5 over 1.5 equals x over 90. And then once you have that set up, you can cross multiply and divide. Okay, 2.5 times 90 is going to give me a 225 is equal to 1.5x. And then divide both sides by 1.5. And we end up with x is equal to 150 feet. Okay, for the height of the oak tree. All right, nice little way to do an indirect measurement to figure out the height of the oak tree without actually climbing up it. Okay, that's it for this lesson. Start going to town on the Math Excel, getting your individual practice in, and we'll see you folks later.